Hi, everyone. In this video, we will finally begin our discussion of differentiability of vector fields. In the past several videos, we've discussed the derivative of scalar fields, both with respect to specific variables, with respect to specific vectors, as well as differentiability of scalar fields in general. Now, we turn our attention to vector fields. This will be the only video in which we explicitly talk about derivatives of vector fields, in part because what we will see is we can use a lot of the tools we have developed around differentiation of scalar fields to help us understand differentiation of vector fields. So just as with scalar fields, one of the first things we want to do if we want to talk about differentiating vector fields is to define the derivative of a vector field with respect to a vector. So just as we did before, we want to consider an arbitrary vector field. So you'll see here, right, the primary difference here, my domain is still Rn, but now I'm considering a vector field. So my range here is Rm, right? So we now have a vector valued function of multiple variables. So I have a vector input or a multivariable input and a vector output or a multivariable output. And I'm going to let A be an interior point of my domain S. Again, this is just going to make sure that this limit is well defined. And let Y be a fixed vector in Rn. So this is the vector I'm going to take the derivative with respect to. Then I'm going to define the derivative of the vector field F at A with respect to Y in exactly the same way we did it for a scalar field. The only difference here now is that I have a vector field instead of a scalar field. And then we should be a little careful to make sure when you start changing types of things, we do need to take a little care to make sure everything is still defined if we do that. So in particular, right, I have that the derivative of f at a with respect to y is the limit as h goes to 0 of f of a plus hy. Now a and y are still both vectors in Rn. For sufficiently small h, because A is an interior point, this will be in the domain of F. And so F of A plus HY will be defined. F of A will be defined because A is in our domain S. This difference will be defined. Okay. But now the primary difference here is that this difference is now a vector quantity. F of A plus HY and F of A are both vectors in Rm. So the difference here is a vector quantity, and I have a vector quantity divided by h, and h is a scalar quantity. So you could sort of object to this at first by saying, well, you can't divide a vector by a scalar. And in some ways you would be correct, although we can make sort of a small definitional thing here. If I write a vector divided by a scalar, what I really mean here is that this is the limit as h goes to 0 of 1 over h times f of a plus hy minus f of a. Okay. So when I write divided by h, I'm really just saying multiply this vector quantity by the scalar 1 over h. And I can multiply a vector by a scalar, right? That simply means that I multiply each component of the vector by that scalar. Okay. So certainly that can make sense. Okay, so this is our definition for the derivative of f at a with respect to y. Now, one quick notational note before we move on. It can be a little hard to distinguish. I think you can, but you just have to pay attention. Right? Notice here that I'm now using bold for f because f is a vector field. A is a vector, so it's in bold. A has always been a vector, so it should have always been in bold. But I'm using bold now to represent these quantities, which are vector quantities. So again, here, this is now the limit of a vector quantity. Now, what does that mean, right? Well, it really just means look at the limit of each component, right? So the other thing that can be helpful at times, and that we'll do several times throughout this video, is to think about what this means component by component, right? So f, if I sort of think about what f is, f, the vector field, right, is made up of different component functions. Okay. So imagine, for example, right, just f of xy is equal to x times y times x squared, comma, x squared plus y squared. So right here, I'm imagining, right, I have an input in R2, I have two inputs, and I have two outputs, right? So an output vector in R2. I have this component function, but notice that this component function here, F1, it's really just a scalar field, right? It takes two inputs, x and y, but it spits out, this component function just spits out a single real value. It spits out a scalar. So I can think of this vector field as being made up of m component functions. Now, we say that because when I come back over here and think about analyzing this, if I re-express this in terms of the component functions, what I'll find is that this is the limit as h goes to 0 of, well, this is going to get multiplied into each of the components, okay? And I'm going to have to do some component-wise subtraction. But what I'll get is I'll get f1 of a plus hy minus f1 of a over h. That'll be the first component of this vector. The second component of this vector would be f2 of a plus hy minus f2 of a over h. So on and so on, all the way up to the mth component, right? Because f has range Rm. So all the way up to f sub m of a plus hy minus f sub m of a all over h. But now you're going to take a limit of this as h goes to 0. And so if I look at each of these, okay, as h goes to 0, I'm going to take a limit of each component. Well, this is just going to be the derivative of the scalar field f1. It's just the derivative of the first component function at a with respect to y. As h goes to 0, this term approaches, this is the derivative of the scalar field f2 at a with respect to y. All the way up to the derivative of fm at a with respect to y. So what we're seeing here is that really, yes, we use the same limit definition, but what it really gives us is that the derivative of a vector field at a with respect to y is just take the derivative of each component at a with respect to y, and this is really just the derivative of a scalar field with respect to the vector y. Okay, so in fact, this exists if and only if each of these exist. Okay, so this is the first sort of case we're seeing where really all of this stuff about vector fields, you just treat it component-wise. Okay, now that's not to say that there's sort of nothing new to learn here. There are some new things to learn because we'll be able to express things in different ways because we're dealing with vectors instead of scalars now. And we'll see that a little bit more towards the end. But to start with, what we're seeing is that a lot of this we can really think of as being very similar. We're just treating the vector field in terms of its scalar component functions. All right. So now, in exactly the same way we did for scalar fields, we can define what it means for a vector field to be differentiable. Now, as you might imagine, right, it does not necessarily mean that all of the derivatives with respect to every vector y exist, right? In the same way that differentiability of a scalar field didn't mean all the directional derivatives exist. It needs to mean a little bit more than that. And the same is true for vector fields. So a vector field, f, is differentiable at a point A if, and again, this is all going to look very familiar with some small changes, there exists a linear transformation T sub A. Now, this linear transformation needs to be from Rn to Rm such that f of a plus v is equal to f of a plus this linear transformation t sub a applied to the difference, the difference vector v, plus norm of v times e of av, where this function e of av goes to 0 as v goes to 0. Now, again, some things have changed, so let's be careful about this, right? Now f is a vector field. This is a vector in Rm. F of a is a vector in Rm, hence why we need this quantity to be a vector in Rm, right? So we're saying that T sub a takes vectors in Rn, V is in the domain, so or is in the domain space, so it's in Rn. And so it takes that vector in Rn and turns it into a vector in Rm, which is good. I need this output to be in Rm. Now, similarly, that tells me over here, norm of v is going to be just a scalar, because the norm's just going to spit out the length, right? And so I need this to also be a vector field in Rm, right? Its range needs to be Rm. So it takes a and v, which are both in Rn. And what I want is a is fixed, but as v goes to 0, then I need this vector quantity to approach the 0 vector, right? Now, again, we're not going to calculate a bunch of things using the definition here, but what I want you to see is that we're using exactly the same definition as before. We're just changing things so that we are now dealing with, in fact, a vector field. We're just changing some small bookkeeping to make sure we carry this forward. Now, unfortunately, this does not have the nice same notion of like a nice approximating tangent plane that we had for like scalar fields. But again, it is this first order Taylor approximation. And really what all of this is saying is that the function can be fairly well approximated by some sort of linear object, right? So this linear transformation is a good first order approximation of this vector field. That's what all of this, that's really what differentiability in general gets at. Is there some nice first order approximation of this object? So this, in this case, our linear transformation T sub a is that first order approximation. Now, of course, the question becomes, well, how do I write this down, right? Like what is this object, right? How might I write it down? And we will see that we can in fact calculate this, assuming our function is differentiable, we can come up with a nice representation of this linear transformation in terms of other familiar objects. So before we get there, though, I do want to point out that this is still sort of the right definition of differentiability. With this, you can prove that if your vector field is differentiable at A, then your vector field is continuous at A. I'm not going to prove that because the proof is almost identical to the case of the scalar field. Okay, so if you check in Apostles' book, all this material is in chapter 8. But if you check in the section about vector fields, you will see that the proof is identical. Okay, so we still get this nice result, right? And remember that this result was really what we were after when we were trying to figure out a sensible way to define differentiability, right? So we spent all this time trying to figure out what should differentiability mean so that we get a result that says differentiability implies continuity, right? That's how we knew, for example, that the existence of all the directional derivatives couldn't possibly be the right definition of differentiability, because we saw examples where all the directional derivatives existed, but the function wasn't continuous. Okay, so again, this is for vector fields. The same idea carries over, that this is the right definition of differentiability and that differentiability will imply continuity. Now, let's go back and think about sort of how we might calculate some of these things. So we looked earlier, right, at this, the derivative of the vector field with respect to a vector y at a point A. And I'm expressing it here in maybe a little bit of a strange format. So let's spend a little time. We're going to walk through this derivation line by line. So if I just go back to what I had written earlier, right? Earlier we sort of said, well, this is really equal to F1 prime AY, F2 prime AY, all the way up to FM prime AY. Okay. So earlier we had said, well, this is equal to this. Okay. And now recall, this is now the derivative of a scalar field. And we know that if this is differentiable, one of the things we saw in the last video is that we could actually express this as the gradient of this function at A dotted with the vector y. So for each of these things, I could go through and I could denote them as the gradient of Fm of that component function at A dotted with y. Now, I can then decompose that into each component. So like if I come up here and write this out, really what this is saying is this is a sum for k equals 1 up to m. So the first term is just the gradient of f1 at A dotted with y. So that's a scalar quantity times the vector E1. E1 is just 1, 0, 0, 0, 0. Plus, then you get gradient of, so now k is 2, f2 at A dotted with y. Again, this is a scalar quantity, but I'm going to multiply it by E2, which is this vector. So notice that what I'm really doing is I'm doing exactly the same thing I did here, right? I'm just decomposing this into the standard basis. Okay. Now, all right. So this first step really is something we've already done. It's just expressing it in a slightly different way. Now, from there, right, I guess you can see I've actually sort of recombined this here. Okay. And if I look at this, this is a vector. Its first component is gradient of f1 dotted with y. Second component is gradient of f2 dotted with y. Every component of this vector is some vector dotted with y. I can therefore re-express this as a matrix multiplication. And so what I'm going to do is I'm going to express this in this first row. I have the gradient of f1. Remember, that is a vector in Rn. And I'm thinking of this as being a horizontal vector. So the first row has the n entries in the gradient of f1. The second row has the n entries in the gradient of f2, so on and so on and so on. And so right when I take this product, it's row by column, right? So it's gradient of f1 dotted with y. The second, which is what I want, the second entry would be gradient of f2 dotted with y. That gives me that. Okay, so I'm just taking this and re-expressing it as a matrix multiplication. Well, let me express out what is this vector? What is the gradient of f1? Well, the gradient of f1 is the first component is take a derivative with respect to the first variable of f1. Second component is take a derivative of the second variable of f1. Up to the nth component is take a derivative with respect to the nth variable of f1. And then I repeat that for the function f2, f3, f4, f5, all the way up to fm. So what I end up with is that I can express, if f is differentiable, I can express the derivative of my vector field with respect to a vector y as this matrix times y. Okay. Now, you might go, okay, great. Well, sort of why do I care about this? Well, if you look at this, in some ways, this is like the generalization of a gradient. So what a gradient is for a scalar field, this matrix is for a vector field. This matrix encapsulates all of the information about all of the partial derivatives of all of the component functions in your vector field. So this sort of encapsulates all of the partial derivative information you could want into one quantity, okay, into this matrix. Okay. And then we can express, just as for scalar fields, right, we express the derivative of a scalar field with respect to a vector as the gradient of that scalar field inner product with that vector. Now here for vector fields, we can express the derivative of a vector field with respect to a vector y as this matrix times that vector y. Now, as you might either recall from a Calc 3 course, or as you might just sort of guess from how long we're talking about this, this is a pretty important matrix, and it's important enough that we give it its own name. This is called the Jacobian matrix. So if each of the partial derivatives, so let's say it's d sub j of fi of a, exists for each I between 1 and m and each j between 1 and n. So basically, if all of the partial derivatives with respect to each variable of each of the component functions in f exists, then we can define the Jacobian of f at a, which will just denote capital D f a. And this is the m by n matrix whose ijth entry is just the derivative with respect to the jth variable of the ith component function of f. Okay, so written another way, right, it's just the Jacobian is just exactly that matrix we saw a minute ago, right? This is the Jacobian matrix. Now, right, if you want to just sort of quickly make sure you can wrap your head around that, say f of xy is equal to, let's just use that example from before, x times y times x squared plus y squared. If you want to calculate the Jacobian, and let's just say at an arbitrary point xy, so f for an arbitrary vector x there, then what is this? Well, the first component is the derivative with respect to the first variable of the first component function. So the derivative with respect to x of this, of x times y. So that would just be y. Now, this entry is still in the first row, but now in the second column, that's the derivative with respect to the second variable of the first component function. So the derivative with respect to y of x times y. So that's just an x. If you now want to get the second row, now we're looking at the second component function. So in the first column, we get the derivative with respect to the first variable. That would just be 2x. And then in the second row, second column, we get the derivative with respect to the second variable, 2y. And now, of course, right, if you had a particular point, right, you wanted to calculate the Jacobian at 1, 2, right, then you would just plug in x is equal to 1, y is equal to 2. X is equal to 1, y is equal to 2. And there's your Jacobian matrix evaluated at a particular point. Okay. Now, again, if you then wanted to calculate the derivative of this vector field at the point 1, 2, with respect to, say, the vector 1, negative 1, you would just take the Jacobian and multiply it by this vector 1, negative 1. And let's see, what would you get? You would get 2 minus 1, which would be 1, and you'd get 2 minus 4, be negative 2, and there's your derivative. So this Jacobian actually in practice is a really helpful way to calculate these sorts of derivatives, right? It sort of quickly encapsulates all the information you need in order to make computations related to derivatives. Now, what is sort of hiding behind all of this, right, is another result, right? just as you'll recall that for scalar fields, right, we were able to say that, well, if you want the total derivative of a scalar field, you would understand that the total derivative of a scalar field applied to a vector y was just the gradient dotted with y, assuming that it was differentiable. Well, we get the same thing here, right? So if f is differentiable at a, then for any vector y, what this linear transformation, so remember, the total derivative is a linear transformation. Sorry, the total derivative of a, let me be a little more precise. The total derivative of a vector field from Rn to Rm is a linear transformation from Rn to Rm. And what we can say is that this linear transformation acts on y in exactly the same way that multiplying y by the Jacobian does. So really what we're saying here is that every linear transformation from Rn to Rm, because we have standard coordinates, we can write down a matrix for that linear transformation. So really what we're saying is here the Jacobian is that matrix of the linear transformation, which is the total derivative. Okay. So it's easy in this context, and not particularly harmful, right, to sort of conflate the Jacobian and the total derivative. Okay. We should be a little bit nuanced about it, because if you go on and study other types of analysis, you might want to take derivatives of things that aren't necessarily vector fields. They might be operators that work not between finite dimensional spaces, but infinite dimensional spaces. And you want to generalize the notion of derivative. And the total derivative there should still be a linear transformation, but because it's now on an infinite dimensional space, you might not be able to write down some nice matrix, or even if you can write down some matrix like this, it may not be the matrix that actually is that linear transformation. So I want us to be a little careful that the total derivative is a linear transformation, because it's, in this case, a linear transformation from Rn to Rm. We can write down a matrix which gives us that linear transformation, and that matrix is just precisely the Jacobian matrix. So if you know your vector field is differentiable, then this total derivative really is just the matrix of partial derivatives. It's the Jacobian matrix. Now, this has some other nice features, okay? And so what I want to close with is actually sort of looking at what the chain rule looks like. We didn't talk about the chain rule for scalar functions. We'll talk about it here for scalar fields. We'll talk about it here for vector fields. And we're not going to prove it, but I just want to sort of think through what's going on here. The proof actually is understandable and fairly straightforward. It's on page 272 of the textbook by Apostle. So if you want to go check it out there, I would strongly encourage you to do that. It's just playing around with the definition of derivative and plugging some things in and comparing things appropriately. But the chain rule says, let F and G be vector fields such that the composition, so F composed with G, is defined in a neighborhood of a point A. So this first part is just setting up, right? You imagine you have, so we're going to deal with a composition here. So you're starting with some point A, right? You're feeding it into your function G. It's going to spit out G of A. And then you're going to plug that into your function F, and that's going to spit out F of G of A, right? And by writing it in this way, what they're sort of avoiding is, right, you need to make sure, like, if this is Rn and this is Rm, then F has to be a function from like Rm to Rl, and then this composition function H that you want, it's going to be a function from like Rn to Rl, and you need to make sure that G of A is in the domain of F. Like, there's a lot of details here they're sort of avoiding in this first sentence by just saying, hey, make sure everything's defined so that all of this will work. Okay, that's really what they're getting at, is make sure the dimensions of ranges and domains match where they need to, make sure the image of G and the domain of F overlap appropriately, right? So that this function is defined on some neighborhood of A. Okay. So they're basically just saying make it work. Okay. All right, now we get to the real assumption. So assuming everything is set up appropriately that these functions make sense, if we assume that g is differentiable at A with total derivative g prime of A, so notice here, instead of writing t sub A, that t notation is not good when you have different functions because it gives you no way of telling you which t goes with which function. So we're just going to call the total derivative of g at A, g prime of A. We're going to let B be g of A, and we're going to assume that F is differentiable at this B. So F is differentiable at g of A, because remember what F is seeing coming in is g of A. Okay, so I want F to also be differentiable at g of A with total derivative F prime of g of A. Then we can conclude that H is differentiable at A, and the total derivative, H prime of A, is given by H prime of A is equal to F prime of B, or like F prime of G of A, composed with G prime of A. And this is just the composition of these two linear transformations. Now, if you think back to, Calc 1, when you first saw the chain rule, right, you probably saw it expressed as something like this. The derivative of f of g of x is equal to f prime of g of x times g prime of x. And if you look here, right, this is g of a, right? So this really sort of looks like f prime of g of a, but this is composed with g prime of a. This was times g prime. So what's going on here? Well, the first thing to notice is that when we're talking about, these are really just scalars, right? So these linear transformations were just multiplication by scalars. And if you compose multiplication of scalars, it's just the product of the two scalars. So while this is written as multiplication, it really is composition, okay, seen another way. Here, we need to use composition because what are each of these objects? These are each total derivatives. What are total derivatives? Total derivatives are linear transformations. Okay? So we realize the linear transformation that is the derivative, the total derivative of h at A by composing the linear transformation, which is the total derivative of f at g of A, with the linear transformation that is the total derivative of g at A. Now remember, back to the Jacobian business, because we're dealing with vector fields here, and because these are all linear transformations between finite dimensional spaces, we can actually represent each of these by a matrix. And so what you actually also can get here, right, this total derivative, right, this can be represented by the Jacobian of H at A. This has some matrix representation. Now, each of these has a matrix representation for its linear transformation, but recall that when we compose linear transformations that are given by matrices, that's the same as multiplying the matrices together. So really what this is the product. So this is the Jacobian of f at g of A times the Jacobian of g at A. Okay, where again, each of these are sort of appropriately sized matrices, right? So you have to be a little bit careful about making sure that the dimensions of all these things match up. So like before, if I had G and then F, right? And this is taking an input in Rn to Rm. This is taking something from Rm to Rl. And then H is operating here, right? This, the Jacobian of G, right, is going to be an M by N matrix. The Jacobian of F is going to be an L by M matrix. Okay. And notice these inner dimensions match, which is good. So the products match. And my output right over here is going to be an L by N matrix, which is exactly what H maps from Rn to Rl. So the derivative, the Jacobian matrix should be an L by N matrix. Okay. So what we see here is that we get a chain rule. Again, you can see the proof in the book of sort of how this is derived. But then that chain rule nicely translates over into something about if I want the Jacobian of H, that should be the product of the Jacobians of F and G evaluated at the appropriate points. So what I hope you've seen here is that while notationally and computationally, things with vector fields can require some more tedious accounting, right? We have more components to deal with, more things to take care of. Fundamentally, we're not changing the definitions. And so a lot of the results that we see are essentially analogous to that we see for scalar fields. So we'll sort of conclude our discussion of vector fields for the time being here. And what we've seen so far is really a discussion of sort of first derivatives, right? We've seen first derivatives of scalar fields, first derivatives of vector fields. And our next question will become, well, what about second derivatives? What can we say if I want to take, say, a derivative with respect to the same variable multiple times? Or what if I want to first take a derivative with respect to one variable and then a derivative with respect to another variable? How does that work for multivariable functions, and what sort of things do I expect? So that's where we'll be moving in the next video.